Okay, welcome back to Feedback Control Systems. This is Module 8.3, Refining the Root Locus. The objectives of this module are to look at real axis breakaway and break-in points of the root locus, define the j-omega crossings of the root locus, look at angles of departure and arrival of the root locus plot, and then finally we're going to plot and calibrate the root locus through some examples. So first we'll start with the real axis breakaway and break-in points. What we have plotted in the S-plane is an example root locus. You'll see two poles and two zeros. The two poles, one at -1, one at -2. And as the gain k starts from, say, 0 and starts to increase, what happens is the root locus starts at those poles, gradually makes them come together, and then they will go off axis. We call that point right here sigma 1. And we'll call that our breakaway point. Now, as we further increase the gain, those two poles will go off axis, and where do they go? As k approaches infinity, they want to go towards the zeros. So that's going to go to the two zeros, which we have 3 and 5, and then they're going to migrate towards the zeros as k approaches infinity. Where that root locus crosses, hits the real axis again, sigma 2, we're going to call that the break-in point. Okay, so we're going to look at methodologies to solve that breakaway point, and in this case, the break-in point. Given those poles and zeros, we can write an open-loop system representation of that, k times gh, just based on the pole and zero locations as shown here. So we have the two zeros as shown here, 3 and 5, and the two poles at -1 and -2. We multiply those out, we get a final representation here, a second order numerator and a second order denominator. Assuming our h is a unity feedback gain system, h equal to 1, we can basically just kind of make that as an assumption. Now, we saw a previous module that if we to satisfy this condition, kgh, if we set that equal to -1, then we know that pole, that test point, if you will, s, equals negative sigma. We know that that's on the root locus because we're satisfying that condition, kgh equals -1. So what we're going to do is this test point, if you will, we're going to substitute that s equals negative sigma into that equation. We get this result here. Set that equal to -1. And then what we're interested in is solving for k. So what we're going to do, rewrite that in terms of k. And now what we want to do is solve for the breakaway and break-in points. And so what we'll do is, again, with k, what is that? That's our gain. When we start at k sort of at 0, we're starting at the two poles, -1 and -2. As k is increasing, where is that point, sigma 1, where they sort of break off axis? At what location? Well, a plot that we're going to show you down here is we can look at k as a function of sigma. So basically this plot down here, as we look at sigma here, we're going to notice two things. First, we'll notice that the local peak here, sigma 1, that's a local peak. And then here we'll notice a local minimum here. And then from calculus, what we could do is set that, take the derivative and then set that equal to 0. So that's essentially what we're doing here, is we're taking this expression of k, taking the derivative of k with regard to sigma, setting it equal to 0 to find that local maximum or minimum, and those are the values of sigma that we can do. So what I would like to do, I'm not going to solve this full derivative for you, but what I'm going to do is the following. So you see the value of k that we have here, but I'm going to write that k in a little bit different way. So I'm going to write my k here as negative sigma squared plus 3 sigma plus 2. So this term, and then instead of writing it as a denominator, what I'm going to do with that denominator is write it as sigma squared minus 8 sigma, and then plus 15. But it's not squared, it's to the, -2. And so now writing it in this formula from calculus, you could think of this term right here as, I'll call this my u term. I'll call this my v term. And when I want to take the derivative, what I can do, it's u times the derivative of v, where I'll use that symbol here for the derivative, u times the derivative of v plus v times the derivative of u. So this chain rule that I can do, this formulation might be a preferred way for you to do this, or we have a u over v. What I find is people don't seem to remember that as well. Certainly if you do, you could use that direct method, but I think most people remember it better in this form. So I would say solve it in this form for the derivative, and you should be able to get this formulation as we see there. If you're struggling with that, by all means, please reach out and we'll walk you through and show you how to do this step by step. So what we can do is, again, set that equal to 0. And really, when we're setting this equal to 0, what are we doing? Well, that term we can cross multiply it by 0, so that goes away. So we're just really setting this numerator term equal to 0. And what can we do? We can use a quadratic formula. When we do that, we see two values of sigma, negative 1.45. Okay, that would be our sigma 1, which is our breakaway point. And then this value right here, okay, that would be our sigma 2, which would be our break-in point. So this is a methodology of how to find those two just simply by knowing what? The two poles, the two zeros, and writing this expression here, and then doing some simple differentiation, we can find those 2 points, okay? Now, because of the calculus, again, on paper, this will take a little bit of effort. There is a more, I will call it, modern way. This was the more traditional way as root locus was discovered, but I think somewhere in the early to mid 90s, 1990s, a different approach was discovered, and so it's called the transition method. We'll talk about that. And this transition method, as we can see, all we're doing is equating two summations. We're summing essentially zeros on the left, poles on the right, and we're using this as a methodology to find the break-in and breakaway points. So if I look at my example here, I have my zeros at 3 and 5 that I'm showing here, and I have my poles 1 and 2 as shown there. So I'm setting those equal to each other. Now I have one equation, one unknown. That unknown is sigma. Again, I could rewrite these fractions here and a function of sigma, and lo and behold, look what we have here. This was the exact same expression, the numerator on the previous slide, when we took this differentiation right here, when we differentiated k with regard to sigma, that numerator, what we had left, is exactly what we have right here. And so what we could do is directly solve for that sigma, again, quadratic formula right there. We get the exact same result as with the differentiation, but now what we didn't have to do is differentiation. We actually just wrote summations as shown here, and then solved basically using algebra. So this method, I think, tends to be a little bit easier for students to comprehend without the need of having to do the calculus method. Next, we're going to look at, so we looked at the breakaway and break-in points. Now, what we saw in that previous root locus, let's just go back, there's at some point where that root locus crosses the j omega axis. Why is that important? Well, when those poles cross that j omega axis, what happens to the system response? The system response goes unstable. So we really don't want poles to be over here. If they're in the right half plane, we know our system is unstable. So we want to stay away from there. We are very interested in what value of k will result in that j omega axis crossing. So here's an example. You'll see the poles and zeros as shown here. This, again, is our open loop transfer function. We can derive our closed loop transfer function T of S as shown there. Unity gain feedback, again, leave it to you to come up with this. Now, one method that we used in previous lectures to talk about stability was the use of this Routh table. So we're going to do a quick review of constructing that table. We take our highest order term, S4, and then what we do is we skip every other term. So here we have a 1. Then we skip the next term. Then we have a 14. We skip a term. Then we have 3k. Then the next is we look at this S3 term right here, and we take the first term, which is 7. We skip the term, and we get the next term, which is 8 plus k. Okay? And then we've completed the first 2 rows of our Routh table. Now the next term here is our s squared term. So the question is, do you remember how to get that term? Well, what we did was our sort of cross multiply. So let's get rid of our ink here. And what we did to obtain this value was we took 8 plus k, that value. Okay, so I'll write that down. So we have that product, 8 plus k, and that's times 1. Okay, that's 8 plus k times 1. We then cross multiply here. 14 times 7. So then we subtract 14 times 7. Okay, so that was essentially our determinant, and there was a negative sign in front of that. Okay, so to solve this, we have a negative. So that's just 8 plus k. And then minus 14 times 7 would be 98. Okay, so here, next what I have is my negative sign. 8 minus 98 would be k minus 90. And then once I get rid of that negative sign, that will result in 90 minus k, which is what I have circled right there. So remember that determinant. Now, when I go to this next term here, notice what happens. Well, I can essentially put a 0 there. And then what I need to do is I cross multiply this term. So let's get rid of that ink. Be a little cleaner here. So I would put a 0 in right there. So to get this 21k term, I would go 1 times 0, which is 0. And then, so that would be that first term, 0 minus, and then I have 3k times 7. So that'd be a minus 21k, but then this minus sign gets rid of that, and I'm left with 21k. So again, I did the S2 row for you. You can continue down the Routh table and get to your S0 term as we show there. Now, as a reminder, when we looked at the Routh table, we said imaginary roots are possible. Okay, so on the geometric axis, they are possible when I have a full row of zeros. Well, if I had the first opportunity that I have for this row of zeros here would be this term right here. Okay, and so I have that highlighted. So if I were to set that equal to 0 and solve for k, I can get a value of k. Okay, and then what I could do with that is now go back to my s squared row right there. Okay, with that value, so my s squared term, so I have a 90 minus k s squared right there. Okay, then the next term is plus 21k, which is right there. Okay, and then if I sort of work that out and then substitute the value of k that I had found previously, I can actually find where on the j omega axis for that value of k that my poles will exist. And so you can see right there at plus or minus j 1.59. And so what we can say is our system is going to be stable when k is less than that value of 9.65 and it crosses at 9.65. So here's another way of saying it. If I were to plot all of these poles right here, a pole 0 mapping, what you'll see is I have a 0, -1, -2, -4, and then I have a 0 here at -3. And if I was to plot that, what we'd see is that as I keep increasing that k, gain k, those poles are going to go sort of migrate away towards the real axis, and that at a gain of 9.65, they will cross again at j 1.59 plus and minus. Okay, so I want to keep my k lower than that to ensure I have stability in my system. So next I want to look at the angles of departure and arrival. So below I'm showing plots of open loop poles and zeros. And first I want to look at what we're going to call angle of departure. And so the angle of departure will be relative to a nearby complex pole. Okay, so here's the approach that I want to take, and then next we'll look at the angle of arrival. So from nearby complex pole. So given this point that I'm circling right there, here is a nearby complex pole, and what I can do, right, is for that point to be essentially on that root locus, I have to satisfy this criteria down here for the angle, right? The sum of the angles has to equal an odd multiple of 180 degrees. So what we'll see as we look through this here is I have a couple of poles. So I have a pole with that angle relative to that point, theta 1. So I have that pole. I have this other pole, theta 4, theta 5. So as I look at my poles, I have a negative, negative 4, negative theta 5. So all my poles have a negative angle associated with it, and all my zeros, theta 3, theta 6, theta 2, here, notice that these all have positive angles. So again, I sum up my zeros, okay? Then I subtract from that the summation of all the poles, and then combine those, and I look at that and say, if the resulting angle is an odd multiple of 180 degrees, then that point here, that point essentially would be on the root locus. And so one thing I can do relative to the angle of departure of that first pole relative to theta 1 is I can do basically what I just said and solve for theta 1. What is the angle of departure from that one pole, theta 1, to that test point? Okay, and so I can actually solve for theta 1 given the other pole and zero locations, knowing that I also have that criteria of a multiple of 180 degrees. Okay, and so that will be this angle of departure. Now, for the angle of arrival to a nearby complex 0, so here is a point, here is the nearby 0. Okay, and so now I'm going to take a very similar approach. If you look at this equation down here, compare it to this equation, you're going to see essentially the identical equation. But in this case now, what we want to do is we want to solve for theta 2 because that's the angle of arrival to the complex 0. So again, remember, relative to poles, the root locus leaves the pole, so that's the angle of departure away from the pole. And then the zeros, that's the angle sort of arrival. It's approaching the 0 as that gain k gets bigger and bigger. So this is a methodology of how to solve those two angles, theta 1 and theta 2, assuming that sort of that test point is very close to either a complex pole for the angle of departure or a complex 0 for the angle of arrival. Next, we're going to plot and calibrate the root locus. Here is our open loop system again, a example that we've used in this module. And what we want to do is using our root locus, basically our open loop poles and zeros, we want to find our value of k to obtain a damping of 0.45. Okay? So the approach that we're going to take to do this is, well, if we know the damping, 0.45, we know from our previous analysis in the S-plane that it's a constant line. So we have a constant line of damping here. And how do we know that 0.45? Well, essentially, we know this angle here. The cosine of that angle would be that damping ratio. Okay, so we could actually find that, solve for that angle, and then that angle, that line would be relative to that angle. Cosine of that theta relative to the imaginary axis, that angle right there, cosine of that angle, that would be your damping of 0.45. So we know that line. Anywhere that we are on that line, if the root locus is somewhere on that line, then we know we can achieve that. Okay, so first we draw that line in the S-plane. And then what we do is we search that line where the sum of the angles for all the poles and zeros, right? We have our 0 here of -3. Then we have our 4 poles, one at 0, one at -1, -2, -4. So with those 4 poles, that 1, 0, we look at that summation of the angle, and then where on that line they sum up to 180 degrees, we know we have it. Okay, so what we can do is we can just take some different values and actually solve for that, and that's what you see in this table here. Okay, and the various r's, again, you can think of that as a radius r. That's basically some vector distance away from the origin here. Okay, let me clear some ink. Okay, so the value of r, you can see different r's of 0.4, 0.5, or 1, or 1.5, etc., or 2. So this first test point of 2, notice this test point of 2, the summation of the angles is negative 251.5. Clearly, that's not an odd multiple of 180 degrees, so that point is not on the root locus. However, what we see in green here is there is a point, a radius of 0.747, where we can get the angle of 180 degrees. And so how do we solve for the gain? Okay, what we do is we take the product of all of the poles, which are in the numerator. So if we know the lengths, so in this case A, this other pole C, this pole D, and that pole E, we take those lengths, multiply them together, the product of the pole lengths in the numerator, and then we divide it by the length of the 0 in the denominator. Again, I don't have these values listed here. You should be able to calculate them as we had shown you in previous modules, so I will leave that for you to do. And in this case, we get a value of k of equal to 1.71. So at that value of k, we know we have we've achieved a damping of 0.45. So let's clear that ink real quick. Okay, so at a radius of 0.747, maybe we are somewhere around here. Okay, and so at that value of gain k, okay, we are that point, that red point, and we have that desired damping. Okay. So that will conclude this module. If you have any questions on any of this material, please don't hesitate to reach out. Thank you.